fluid mechanics, and these are the equations that govern the material in different astrophysical situations. Now, there are various other aspects of fluid mechanics which we shall discuss as and when required. In today's lecture, we shall move on to a different topic. Much of our information about astronomical sources comes through the study of electromagnetic radiation. Practically most of it comes through the study of electromagnetic radiation. Some information does come through high energy cosmic ray particles and some through neutrinos, but the bulk of it is through electromagnetic radiation. There is currently a great effort underway to study gravitational waves, and if that is fruitful, then that shall open up another window in astronomy, gravitational wave astronomy. But right now much of astronomy deals with electromagnetic radiation. So what is this radiation? We all know that electromagnetic radiation is essentially an electromagnetic wave, and I will briefly summarize the salient property of this wave. So if the wave is propagating along the x axis, then we have an electric field oscillating the electric field pattern in the direction perpendicular. We have an oscillating electric field pattern in the direction perpendicular to the x. So if I sit at one place and see the electric field, it is going to oscillate up and down possibly, and the magnetic field is always orthogonal to both the direction of propagation and the direction of the electric field. So this is in general what we mean by an electromagnetic wave. There is a direction of propagation and we have an oscillating electric field pattern that moves along the direction of propagation. The electric field is always orthogonal to the direction of propagation. There is also a magnetic field, which all three are mutually perpendicular, and the electric and magnetic fields both oscillate with exactly the same phase. Okay. And this is a transverse wave. The electric field can oscillate in any direction in the plane orthogonal to the direction in which the wave is propagating. Okay. And the magnetic field is always perpendicular to E. So this brings about another aspect, that is polarization, but right now we shall not touch upon the polarization of the electromagnetic wave. Having told you this much, that it is a wave with a transverse wave with the electric field oscillating perpendicular to the direction of propagation, and this oscillating electric field pattern propagates. And we can have electromagnetic waves of a variety of wavelengths or frequencies, and all of them are important in astronomy. So we gather information about astronomical, about sources, about the universe in the entire electromagnetic spectrum, and the different parts of the spectrum have been given different names. So let me just briefly, and they have different properties also, let me just briefly go through this. The lowest frequency electromagnetic waves. Okay. So if you look at this diagram, the frequency reduces as you go along this direction, or the wavelength increases. We know that they are inversely related, and they are related, the constant with the constant, they are related through the constant, the speed of light. Okay, so as you move along this axis, the frequency goes down or the wavelength increases. And the largest wavelength or the lowest frequency electromagnetic waves below 1 gigahertz, these are referred to as radio waves. And between 1 gigahertz and 3 into 10 to the power 11, or say between up to 1 millimeter roughly, we have microwave. Okay, so the lower part of the spectrum is essentially radio and microwaves. and the Earth's atmosphere is transparent to a large range of wavelengths in this frequency band, in this band. Okay. The lower part is cut off by the ionosphere. The atmosphere, we know the upper layer of the atmosphere there is an ionized layer where there are free electrons and protons, free electrons and gas ions, not protons, free electrons and proton ions, and any electromagnetic wave of a low frequency coming through that is reflected, or there are transmission effects, the intensity is attenuated considerably. Okay, provided you are working at very low frequencies. So this cutoff becomes important at frequencies say below 25 megahertz or 30 megahertz, 20 megahertz or so, below that. Okay. So if you look above 20-30 megahertz, you can do astronomy, you can look outside the atmosphere, and you have a transparent window, and if you keep on increasing the frequency or decreasing the wavelength, again over here at high frequency, at the high frequency end of the microwave or the low wavelength, say around 1 millimeter over there, you start getting molecular transitions in the atmosphere. There are water molecule, carbon, various other, carbon dioxide, carbon monoxide, all these molecules in the Earth's atmosphere. So they have rotational and vibrational levels, and the energies of these levels corresponds to frequencies in this range at the higher end of the microwave and in the infrared. So much of this is that the Earth's atmosphere is opaque to much of this. Okay. There are bands where you may observe, but largely there are water vapor lines and various other lines here. Again we have a transparent window in the visual region where our eye is sensitive, and there is you can do terrestrial astronomy over here. Some parts of infrared also you might be able to do from the Earth, or if you go to very high altitudes you might be able to access them. Okay. Ultraviolet is blocked off fortunately because the sun emits copious amounts of ultraviolet, and this is harmful to life on Earth. X-ray and gamma rays are also blocked by the Earth's atmosphere. Okay. So if you want to study these other bands, you then have to send satellites outside the Earth's atmosphere. Okay. They are heavily attenuated by the Earth's atmosphere. You could study gamma rays on the inside the Earth from secondary showers. Okay. And one thing that we should bear in mind, so much of our information about astronomical objects outside the Earth is gathered by the study of the electromagnetic waves coming at different frequencies from that source. Okay. And the same source may look quite different when you look at it in two different frequencies. Okay. So it is a frequency dependent fact what a source looks like. For example, in the last class we looked at the sun, and we saw that in the visual the radiation comes mainly from the photosphere, the surface of the sun, and that is a temperature of around 5800 Kelvin. If you look at the sun in X-ray over here in X-ray, then we saw that it is not the photosphere, the surface of the sun actually is darker, relatively dark compared to the corona which is outside the sun, which is much hotter, and where the bulk of the X-ray radiation originates. Okay, so you have an entirely different picture of the same region of the sky, of the sun. Okay, so if you look at the any astronomical source in different parts of the spectrum, you may get totally different images and totally different information, and possibly you may need all of the information to really get a picture of what is going on there. Okay. So with this, and you have telescopes now which operate in nearly the entire across the entire electromagnetic spectrum, and which gathers information about the techniques used are maybe different in different parts of the electromagnetic spectrum, and using these telescopes one can gather information about sources at different parts of the spectrum. Okay. So now having given you this background, let us now go on to the study of this electromagnetic radiation. So, we have just heard that it is a wave. Okay. Now, if you are dealing with length scales which are comparably larger, so if you are dealing with length scales that are much larger than the wavelength, which we do typically in astronomy, astrophysics, the length scales are enormous and the wavelength is quite small, as we have just seen, could be millimeter, centimeter, meter, and could be Armstrong, right. So, in most of these situations, it is adequate to think of light as, forget about the wave nature of light and think of light as rays. Light propagates in a straight line along rays. Okay. So, it is adequate to think of light as rays along straight lines along which light propagates. This is geometrical optics. So, in our discussion today, we are going to adopt this picture that light propagates in straight lines along rays. The wave nature is not important. It becomes important only when we look at length scales, when we have length scales which are comparable to the wavelength of light. Okay. So, let us, for our discussion, consider the simplest possible situation where we have an astronomical source here that emits radiation isotropically. So, this is an isotropic source. And it has a luminosity L. So, this is the luminosity of the source. By luminosity, we mean the energy that it emits in per unit time. So, it is in, you can measure it in watts power. Okay. So, it emits an energy L per unit time. Now, if there is an observer at some distance r from this source, so that let us consider an observer over here, and this observer asks the question how much energy crosses a unit area placed normal to this direction in which the light is coming. So, the rays are coming from this direction. The observer places an unit area over here and he asks the question how much energy, what is the flux? This is the energy coming per unit area per unit time. This is what a distant observer can measure. He cannot obviously go and directly measure the luminosity. He can measure, he or she can measure the flux over here. You can put a detector and measure the flux. And the radiation being emitted from here will be distributed, since it is isotropic, it will be uniformly distributed over a sphere of area 4 pi r square. So, we know that the flux is the luminosity by 4 pi r square. Okay. And the further away the observer is, the fainter, the less the flux is going to be. Okay. Now, this is the simplest description of the electromagnetic radiation, but it is rather simple because it considers all the rays coming out, right. Now, we shall be interested in a slightly more detailed picture of the electromagnetic radiation. So, we shall consider what is defined as the specific intensity or brightness. This is also referred to as brightness, sky brightness or brightness. Okay, so now in the earlier context we looked at all the rays coming out from that source. Okay, that is a rather crude picture. Now we are here interested in the energy that is carried by a ray, a particular ray, an individual ray. Okay, so this specific intensity is defined for an individual ray. Ray of light. Now it is not meaningful to talk about a ray propagating in a single direction. Okay, so we have, it is meaningful, more meaningful to talk of a ray propagating with a spread in directions, right. So the question that we are going to address is as follows. Suppose we place a unit area detector of unit area over here, normal to the ray, and we ask the question, how much energy is incident. So we are interested in a particular ray. So the question asked is, how much energy is incident in this direction, from this direction. But I have told you that it is not meaningful to ask about a ray in a particular direction. So the question has to be rephrased, what is the amount of energy that is incident in a solid angle d omega on the area dA in the time interval dt. So the question is as follows, what is the energy incident on the area dA from the solid angle d omega, that tells you which ray you are looking at. You are looking at a particular ray in the time interval dt in the frequency interval d nu. Okay, that is the question being asked. This tells you the energy being carried by this ray. Okay, so we are interested in the energy being carried by this ray, and this is given by INU, which is called the specific intensity, into these numbers. So that is how the specific intensity is defined. So let us go through the definition again. The specific intensity INU tells us the energy coming on this area dA from the solid angle d omega, that is a specific ray, in the time interval dt in the frequency interval d nu. So that is the energy coming here. Okay, that is the definition of the specific intensity or brightness, right. And we are now going to study some properties of the specific intensity. So in astronomy or astrophysics, we characterize the radiation using this specific intensity, or it is also referred to as the brightness. So this is a function of direction, okay, also, right. It is in a particular direction, in a solid angle d omega, in this particular direction. Here it is the normal direction. Now what are the units of specific intensity? Let us first look at that. So the left hand side is going to be energy units, say joules, right. That is the amount of energy coming on this. So the specific intensity should have units energy. So let us say joules per first area per meter square, then we have per steradian, steradian is a measure of solid angle, then we have per frequency per time s second per hertz, right. So, that is the unit of specific intensity, joules per steradian. You can order them differently, per second, per hertz, per steradian. Okay. So, that is how the energy carried by a ray is quantified. Good. So, with this definition, let us now calculate a few things so that we get a feel for what we are talking about. Let us first calculate the energy flux on a surface. Okay. So, we are going to first calculate the energy flux. Or just the flux, right, which we just calculated for an isotropic source. So, we will first calculate the flux F, and here it is the specific flux, right, because we are talking about a specific frequency. So, it is a specific flux F nu. Incident on an area like this, whose normal is over here. Okay. Now, a ray coming at an angle, so this area is dA. A ray coming at an angle like this will see a smaller area, it will see the area projected normal to this, right. So, the energy coming flux from a ray coming at an angle is going to be reduced by a factor of cos theta, where theta is the angle that the ray makes with the normal. So, if you want to ask the question, what is the energy coming in this area dA in the unit time dt in a frequency interval d nu, then you have to integrate over all the different solid angles. So, this will be equal to, so the energy coming from any one direction is I nu, from the normal direction is I nu d omega, and if it comes at an angle, it is going to be reduced by a factor of cos theta. So, this gives me the energy flux I nu cos theta into the solid angle, and I nu is a function of the direction in which the light is coming. I nu could be a function of the direction, it could also vary from place to place. Okay, so you should bear this in mind. So, this is the energy flux. Let us next consider the momentum flux. Now, for photons, for electromagnetic waves, for photons, which you can, if you think in terms of photons, the idea is simplest. We know that it has an energy and a momentum both, and the momentum P is E by C. Okay. So, if you can calculate the energy and divide by the C, you will get the value of the momentum. Now, we are interested here in the momentum normal to this surface. Okay. So, radiation incident on this surface is going to impart momentum to this surface, and the momentum imparted, we are interested in the component normal to the surface. So, if you want to calculate, the energy is coming like this, and if you want to calculate the momentum imparted in this normal direction, you have to then put a factor of cos theta. Okay. So, there will be two factors of cos theta, one because you are looking at the particular component of the momentum, one because the area gets projected, right. So, the momentum flux P nu is equal to 1 by C I nu cos square theta d omega. okay, and these are all different angular moments of the specific intensity, right. These are what are called different angular moments. So, multiply with cos theta and integrate over solid angle. This is the first moment, this is the second moment. Okay, so the momentum flux is the second, first moment is the energy flux, momentum flux is the second moment. 0th moment will have no cos theta at all. Okay. Let us next look at the energy density. So, the energy density along a ray. In some region, rather, energy density in some region. Before we look at the energy density in some region, let us first consider the energy density along a ray, which we shall define as u nu omega. So, it is the energy density along, so let us draw a ray here first. And it is the energy carried by this ray, the density of energy carried by this ray, okay, that is given by u nu omega. We are finally interested in the total energy. So, this is the region of, this is the volume that we are interested in. So, the energy contained in this volume dE nu is dV, and there will be a d nu and d omega, right. So, this is because this we are looking at a particular ray, so there will be a factor of d omega, that is a ray in a small solid angle, and this is in a frequency interval nu, and the energy density into the volume will give me the energy. Okay. So, that is how the energy in this particular ray in this volume is defined. Okay. Now, we also know that dE nu is equal to, let us put an area over here, unit area, and we know that the energy flux, energy that will cross this is I nu is dA dt d omega d nu, that is the energy that will cross this area dA. Okay. Now, let us say that this dA has the same area as the area of the volume we are interested in. Okay. Then what is the length over which this energy is distributed? The energy that will cross in a time dt, that length is c dt. So, this volume dV we can say is equal to c dt, okay, into dA. So, if you identify these two, it is quite straightforward that the energy density of a ray is equal to I nu by C. Okay. This is the energy density in this ray. If you are interested in the total energy density, you have to integrate over all possible rays. So, you have to integrate over all possible solid angles. So, this is equal to 1 by C, the integral of I nu d omega. Which we can also write as u nu is equal to 4 pi by C j nu, where j nu is the average specific intensity. What do you mean by the average specific intensity? You integrate it over all solid angle and then you divide by the total solid angle, which is 1 by 4 pi, that is the angular average. Okay. So, the what we see is that the energy density is related to the zeroth moment of the specific intensity. Okay. And you can now also integrate all of these over frequency to get the total energy flux, the total momentum flux, the total energy density, right. These were the specific ones. So, if you for example, you want to calculate the total energy, total flux, not total flux, what you have to do is you have to integrate F nu d nu. Total momentum is going to be P nu d nu. This is a specific momentum, and the total energy density U nu is U is U nu d nu. Okay. So, those were certain properties of the specific intensity. Let us now consider another simple example. Let us consider a reflecting cavity. I have drawn it spherical, it need not be so. Okay. There is a reflecting cavity which is filled with isotropic radiation. Okay. So, it is equal in all directions. The radiation inside is isotropic. So, the radiation goes and gets reflected and then goes again and gets reflected, and it is isotropic inside. This is an example which is going to be considerably important. So, we want to calculate the pressure inside this. So, pressure we know is the force per unit area, and we can write it as the momentum flux, the rate of change of momentum, right. Momentum flux is also the pressure. So, let us calculate the momentum flux in some element over here. So, the momentum flux we have seen is 1 by C into the integral of the specific intensity. This is P nu, let us say, in a particular I nu cos square theta d omega. Okay, that is the momentum that is incident, but this will get reflected. So, there will be a factor of 2 because it is reflecting, right, and the integral here is now going to be only over one direction, only on one incident, only on this half, it will not be on that half. Okay. Now, this integral over solid angle we can write in spherical polar coordinates. I hope you are familiar with this. So, we can write it as 2 by C. So, cos theta, remember, is this angle theta. We also have the azimuthal angle, right, just to get things clear. This angle is theta. This angle can also be rotated like this angle is phi. Okay. So, we can write this as d phi. I nu is isotropic, it does not depend on direction, so it can just be taken outside. So, we have cos square theta d theta, and I have I nu completely outside. Okay. And this integral is from 0 to 2 pi, 0 to 2 pi, and the theta integral only goes from 0 to pi by 2, there is nothing coming from the other side. Okay. So, this goes from 0 to pi by 2. Okay. So, this gives me a factor of 2 pi, and this just gives me, sorry, there will be a cos theta sin theta d theta, right, that is the solid angle. The solid angle is d phi sin theta d theta. Okay. So, if you do this integral, then you will get a factor just 1. Okay, it is a straightforward integral. So, what you get from this is that this is equal to 4 pi 1 by 3, sorry, you have to do, you can just write this as d of cos theta and do the integral. Okay, what you will get is 4 pi by 3 c into I nu. Now, if you also calculate the energy density inside, specific energy density, this is 1 by c, the integral of I nu d omega. Since I nu is isotropic, it is the same in all directions. This is equal to, how much is it? 4 pi. So, integral of a solid angle is 4 pi. So, 4 pi I nu by c. Right. So, this is equal to 4 pi I nu by c. Okay. So, what we get by comparing this and this is that the pressure is equal to 1/3 of the energy density. Okay. This is very important for an isotropic. So, for isotropic radiation, the pressure, radiation field, the pressure is 1/3 of the energy density. So, I request you to please go through this yourself once or twice to make sure that you have really understood it. Okay. So, we have been calculating various properties like pressure, energy flux, momentum flux, etc., using the specific intensity. Now, let us ask the question, how does the specific intensity change as the light propagates? Okay. So, how does the specific intensity change as the light propagates? So, to do that, let us consider first a particular ray. So, okay, and let us look at two surfaces located at two different positions. So, this is one surface and this is another surface. And let us look at two different areas on these two surfaces. So, this is the area dA1, this is the surface 1, and this is the area dA2. Now, I have told you that a ray is not exactly a particular ray does not refer to a single direction, there is a spread in direction. So, let me also draw the spread in direction. So, you could also have something like this, right, a small spread in direction, the whole thing is propagating in this direction. Now, we have drawn these dA1 and dA2 such that all the rays that go through this also cut through this. Okay, nothing more comes in here between here and here. Okay, so this entirely, everything that goes in through this goes through this, the entire ray also passes through this. Okay, that is how we have defined these two areas dA1 and dA2. And the quantity that we are now interested in seeing is how does the specific intensity change as you go from the first surface to the second surface. Okay, that is the question that we are interested in addressing. Right, and these two are located at a distance r apart. So, that is the problem that we are interested in solving. Okay. So, let us calculate the energy that passes through this in a time interval dt in the frequency interval d nu. Okay. So, let us see. So, the energy that passes through this is I nu 1, that is the specific intensity value over here, into dA1 d omega 1 d nu 1, d nu and dt are the same, okay, in the same frequency interval, in the same time interval. This is going to be equal to I nu 2 dA2 d omega, right, because the same rays, the entire ray passes through this area and this area. So, we are looking at the area cut by this ray over here. Okay. Now, let us ask the question, how are the two solid angles related? How much solid angle does this subtend over here? Solid angle we know is the area over here divided by the distance squared, right. So, we know that d omega 1 is equal to, what is d omega 1? It is dA2 by r square, right. That is the solid angle subtended by this angle, this area over here. What is d omega 2? It is dA1 by r square. So, you can see that if I put these two over here, what I have is dA1 dA2 dA1 dA2 by r square. So, all of these factors are essentially exactly the same. So, we are led to the conclusion that the specific intensity at 1 is equal to the specific intensity at the place 2. So, specific intensity is something that does not change when the light propagates in free space. That is a very useful and interesting property. Okay. So, the specific intensity that comes of the radiation from the sun, for example, is the same whether you look at it on the surface just outside the sun or if you look at it here, it does not change. Okay. Let us try to understand now how does this connect with the picture that if you go closer to the sun, you will receive, obviously you will receive more radiation, right. The specific intensity does not change, but we know that if you go further away and further away from the sun will appear fainter, right. So, let us try to see that this is actually consistent with that. Okay. So, for that again we consider, let us consider a spherical source like this. And this source is an isotropic source with brightness B. So, what we mean by that is all the rays, surface brightness is B, all the rays that leave this have the same specific intensity B. It is an isotropic source emitting with the same specific intensity. So, all the rays that leave this have the same specific intensity B. Okay, that is the source we are looking at. And let us consider an observer at some distance r from this source. Okay. And the source, let us say, has radius capital R. And let us ask the question, so what is the flux of radiation that will be measured by an observer over here? Energy flux, what is the total amount of energy that an observer over here will receive? The flux, that is the flux, right, energy per unit area, that is what we finally measure. So, the flux F is the integral of the specific intensity into cos theta into d omega. Right, where theta is this angle. So, this is the maximum value of theta, theta is the angle that it makes with the normal, this is theta. Okay. So, the radiation is going to be incident for a range of theta starting from 0 over here till a value. What is the maximum value? The maximum value, let us call it theta c. It is going to be sine inverse of this divided by the radius, right. That is where the tangent, this line of sight is going to be tangential to this curve. Okay. So, this is going to be sine inverse r by r. Okay. So, this is the limit. So, you have to integrate over this solid, all solid angles over this disk. So, this will appear like a disk. Each point on the disk will have this brightness, will be emitting with this, will be arriving with this brightness, and I have to integrate the specific intensity over the entire disk to calculate the flux over here. Okay. So, there are two angles involved, one is theta which changes like this, and another one is phi, which if you look at the disk, this is the disk, I am looking like this. So, that will be in this direction, phi. Okay. Now, so we can write this integral, this specific intensity is a constant that comes outside, and we have 0 to 2 pi d phi, that is the phi integral, phi is the angle with respect to some fixed direction, and then I have 0 to theta c, theta c is this angle of cos theta sin theta d theta. Let me remind you that the infinitesimal solid angle d omega is d phi, let me write it somewhere, the infinitesimal solid angle d phi sin theta d theta. Okay, this is how you in spherical polar coordinates this angle is theta, you project this onto the xy plane, take the angle here, this is phi. Okay. And you want to integrate over solid angle d omega, then you have to do the integral d phi d theta cos theta, and the range of theta is 0 to pi, the range of phi is 0 to 2 pi. In this case the range of theta is just 0 to theta c. Okay. And if you do this integral, so this integral you can write as so this integral can be written as minus cos theta d cos theta, right. So, we can now do this integral just gives us cos squared theta by 2, right. So, we have the flux is equal to b pi, and we have if you integrate this you will get cos squared theta with the minus sign. Now, the two limits are 0, are theta c and 0. So, since there is a minus sign I can take the limit 0 first. So, at 0 cos squared theta is 1. So, this becomes 1 minus cos squared theta c, which is sin squared theta c. So, we get b pi r square by r square. Okay, where we have just used the value that sin theta c is r by r. Okay. So, what we see is that the flux indeed falls off as 1 by r square as you go further and further away. Okay. That is the first thing, which is what you expect, 1 by r square. So, the flux is what falls as with distance. Why does the flux fall? the flux does not fall because of a reduction in the specific intensity. The flux from the sun falls off as you go further and further away, not because the specific intensity has gone down, but because the solid angle subtended by the sun actually goes down as you go further and further away. So, for any source, the specific intensity does not change as you go further and further away, the solid angle changes, and it is usually the flux that we measure. So, the flux falls as 1 by r squared. Okay. Another interesting fact is that on the surface the flux is exactly equal to pi into b. Okay. Right. Now, this was all in vacuum. So, in vacuum we saw that the specific intensity does not change as light propagates. Now, what happens inside a medium? Let me very quickly derive the equations for what happens inside a medium. So, let us now consider a ray like this, and it enters some medium. Okay, so this is my medium over here. Once it enters a medium, you can have either absorption, the light can get absorbed, or emitted. Right, you can have emission again at the same frequency. So, there are two processes. There is also scattering, which we can think of as both absorption and emission combination. Okay. So, let us first consider emission. So, we introduce IGNOU, which is the emission coefficient, specific emissivity, okay. So, how is this IGNOU defined? Let us consider a volume of material dV. Okay, so there is a volume of material dV, and the amount of radiation that this volume of material dV emits in this solid angle. So, we are interested in the production of a particular ray. Okay. So, in a particular solid angle, d omega in the frequency interval d nu in the time dt, J nu into this is the energy that is produced by this material. Okay. So, the volume dV of this material produces energy dE nu in the solid angle d omega. So, the energy that is going out in the solid angle d omega in the time interval dt, in the frequency interval d nu. Okay. So, let us now think of this as having area dA, cross sectional area dA, and length ds, del ds, let us say. Okay. So, there is light incident over here, there is a ray incident over here, and the ray comes out from this side. Let us ask what is the incident energy. The incident energy we know that the incident energy is I nu at the point S this is S plus ds into dA d omega d nu dt. Now the amount of energy that gets added over here when it traverses through this, the amount of energy that gets added is plus this thing over here. So it is plus J. Now the dV here is dA ds into d omega d nu dt, and this will be equal to what comes out. What comes out is the specific intensity at the point S plus ds into all of these factors again. So we have dA d omega d nu dt. So we can see that all of these factors exactly cancels out, and you can take this onto the left hand side. So what you will get is the difference in specific intensity is equal to J nu into ds. All the other factors cancel out, okay. Or you can write it in this form, di nu ds is equal to J nu. Okay, that is the radiation that gets added due to emission. Okay. Now let us also consider, okay, I think we are running out of time now, so we shall postpone the discussion of the absorption to the next class. Okay. So we have considered what happens due to emission.